Hello, Shajesh.
Oh, Pipan. Oh, thanks.
Yeah. How are you?
Yeah, doing good. Yeah. So
What is
today,
today's
speaker.
topic like?
Tell that again, Pipan.
What is today's topic like?
It is about friction, how friction is generated between
Okay.
surfaces,
Okay.
and what is the source of that friction.
Okay.
That's what it is.
Okay.
So the speaker actually, he's a high school student,
Okay.
and he started working with me, Prachi, and one more of us, Vijay Kumar. He's in
Okay.
when he was going from his 9th grade to 10th grade.
Okay.
He worked on this for 2 years and recently came to a reasonable conclusion, and there was a small submission he made. So pretty nice, impressive work.
He's still a student or?
He's still a student. He's
12th grade now.
He's now in his 12th grade. Yeah.
Okay. Okay. That's good.
So, but very good. Yeah. Here is. Hello.
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 Good morning. Yes, where it is.
Morning.
Yeah, it is early morning, I guess. Are you used to waking up this early?
Perhaps the past 2 days I usually don't wake up this early. I wake up around 6, but yesterday I just happened to wake up early. So perhaps for 2 days, the case.
Yeah. Good. Did you inform your parents about it? Were they interested?
Yeah, they woke up earlier.
Okay, nice. Good. Hello, Rishi. That's John, I suppose, John Joseph.
Probably.
Hello.
Hello, John.
Yeah. Give me a second to get my camera.
It's okay. Ah, there you go.
He's still sleepy.
Yeah.
Too early down here.
Yeah, I think this time doesn't suit like people around here. Otherwise, there will be people wanting to attend.
Hi,
Oh,
Shajesh.
Hey, Rishi, how are you?
Yes, I'm good.
Yeah. So when the time changes, it gets worse, right? Not better.
No, it gets better.
Yeah.
1 hour better for us, I guess. But is the time changing? I thought the Senate passed something that we'll stay in this time or forever.
You mean we'll always be in daylight saving?
Yeah.
Always in daylight saving, not the other way.
Always in daylight saving. And that was like a weird
I see.
isn't it true, John? Do you remember reading about it? Or Ram, do you remember reading about this? Like Senate passed.
I don't remember
passed
any
it.
bill about it. No, any legislation. I thought it was just going to come in November, or it would end on November this year. So.
Yeah, I don't know when it is supposed to be implemented. This year not, but I think. So the point is, it is going to be. I think it will not stay. Maybe after a few years they will have to go back, because the time is going to be pretty bad during the winter months, and parents are not going to like their kids going early when it is so dark. So if they wanted to fix the time, they should go to the standard time, DST. Like,
So we're at least gonna get an extra hour of sleep before they change it, or they're gonna
Yeah, I don't know.
get that part.
Yeah.
Okay, so it's about 3 minutes down. So,
Ashwati is going to be there or not?
oh yeah, I didn't realize. Yeah, it should be there, but shall we just go and begin anyway? Because she can join, right?
Yeah.
Okay.
Yeah.
All right. Thank
Hello.
you.
So we have Ram Narayanan giving his talk today on coefficient of static friction for van der Waals materials. He's in his he just started his 12th grade in Horace Mann School in Bronx in New York, and he started this project 2 years back, I suppose, when he was when he just started his 10th grade with the three of us, one of them Vijay Kumar in Columbia Medical Center, Prachi Parashar in John A. Logan College, and myself in Southern Illinois University, Carbondale. And he recently brought this project to a reasonable conclusion and submitted it as a paper a couple of weeks back. So let's see what he has to summarize about his project. Go ahead, Ram. Thank you for.
So, is this screen displaying the full screen presentation?
Yes.
So, good morning to the United States. Good afternoon to anyone that's watching. Good evening to anyone that's watching from around the world. I'd like to thank Dr. Chajish at least for helping me set up this talk. It's a really great opportunity, regardless of audience, just putting my work out there for everyone to see. I appreciate it. Who knows where this will be in years' time. So I'm Ram Narayanan. I'm from the Horace Mann School in Bronx, New York, in the United States. And this presentation was mainly about my research, the research on static friction, specifically, as the title implies, the coefficient of static friction in van der Waals materials. But I also wanted to give some background about static friction in this presentation, just because for the undergraduate audience, I assume, I know that's watching, but in case anyone's watching on YouTube on the recording session, I just thought that would be easier. So when we think of the force of static friction, you really don't need to look further anywhere than just your room. If there's an object that's lying on any kind of surface, I have this phone on my table, when you push on it very, very, very gently, it won't move. While that's happening, the force of static friction is applying a force that's equal and opposite to the force that I am applying to the phone. Now, you notice just from intuition or experience that once you push past a certain amount of force, which is generally the same for everything you're trying to push, that's when the phone actually starts to move, and then the situation is no longer static. We have kinetic friction involved instead. And in sort of undergraduate physics, any course, you learn that the maximum value of static friction, the maximum value that static friction can resist however much you're pushing, is given by the equation Fs max is equal to mu s times Fn. And this is an equation from what is called the Coulomb model of static friction. I don't think that name is very popular in terms of like how we just say it in a classroom or a textbook, for example. But yeah, this is the same Coulomb who did the work on electrostatics, Coulomb's law. And just looking at that equation first, regardless of what that quantity mu s times Fn means, what it implies is that if you push with a force greater than mu s times Fn, that is the amount of force that's required to actually make the object slide against the other. And after that, then you have kinetic friction, which is like sort of beyond what we are studying, just static friction. So now actually looking at it, Fn is the more familiar out of those two, which is the normal force. It is the contact force that is pushing the two surfaces together. And mu s is an empirical quantity coefficient that's unique to every pair of materials. So I'm going to demonstrate this on the next slide, but for example, the coefficient of static friction between ice and ice is separate. The coefficient of static friction between ice and aluminum is separate. The coefficient of static friction between aluminum and aluminum is separate. But the coefficient itself is, in this Coulomb model of static friction, only dependent on the materials. Now, I'll show the next slide before I get into the question sort of towards the bottom of the slide, and which is like when we consider everyday static friction. I like to think of it, for example, from the purposes of an engineer. Suppose there's a heavy wooden object on a brick floor. 1,000 newtons I thought was a reasonable weight for something like a sofa. And if someone wanted to understand how much force they had to push with on this sofa to actually make it slide across the force, what they do is, well, they measure its normal force, they'd probably mass it, figure out its weight. And then, if for an engineer's purpose, they would just look up the coefficient of static friction between wood and brick, which is the bottom of the furniture and the floor. And using Fs max equals μs times Fn, they would see, okay, the coefficient of static friction between brick and wood is 0.6, multiplied by the normal force between the two objects gives 600 newtons of force that's required to overcome static friction. This is the sort of very basic definition when it comes to, for example, like doing any textbook physics problems. You use μs in this way to find the maximum static friction force. Now, when it comes to this sort of engineering practice, you're usually just given μs, or you find it from some kind of table. There are tables online. For example, you just search up coefficient of static friction table, and there will be this list that comes up with some sources at the bottom. But it's important to understand that the values that are in these tables are determined experimentally. A classic way of determining that is an incline test, with the result when something just about slips on an incline, μs is equal to tan theta, where theta is the angle of the incline. But there are much more sophisticated experiments, such as like tribombers, which involve like spinning parts and holding one surface flat while the other briefly touches it to measure the force experienced by a bearing that's rotating. But when it comes to a very sort of fundamental understanding of this theory, particularly the molecular fundamental forces that are involved in actually bringing about static friction itself, there isn't a very, very sort of solid basis for this understanding. And when I say fundamental forces, obviously, yeah, I mean gravity, electromagnetism, however you want to call it, but also subsets of these forces. So for electromagnetism, we're considering not just the electromagnetic force, but for example, the electrostatic force, dipole-dipole interactions, the van der Waals force, and the Casimir force, as we're going to get into in this work. And in terms of a practical application of such a theoretical understanding, one of the sort of frontiers in engineering is this nanotechnology and microelectromechanical systems, these very sort of small mechanics or electronics. And one of the biggest obstacles in the development of these is that there's this very large surface area to volume ratio, and when these parts become sort of stuck on each other, that essentially stops the motion of, for example, like a gear within a system. So if it would be possible to engineer the coefficient of static friction between any two surfaces in these machines, that would allow for perhaps a whole new gateway of research to open into new microelectromechanical systems, where this force of static friction is no longer a sort of a very big obstacle. And when it comes to a more scientific purpose instead of an engineering one, obviously the table works for, obviously there's more than this in the actual table. Such a table works for sort of standard household materials, brick, wood, steel, brass. But when it comes to a scientist that's perhaps very sort of finely modified the structure of a certain material, or if there's a new material that's been made by any kind of synthesis, chemical vapor deposition, for example, actually testing the coefficient of static friction requires costly experimental effort in terms of time and resources. If it was possible to just predict the coefficient of static friction, if I could give you a surface of certain atoms, I can tell you everything you need to know from its electronic properties, dielectric properties, its structure, its surface, periodicity, things like that. And you could just tell me right away what the coefficient of static friction was between two such layers. that would allow you to avoid, well, not necessarily like avoid completely, but it would provide a basis for later experiments when you're actually calculating, or sorry, determining the coefficient of static friction empirically. So with that said, we do want to at least ground this in previous literature while we're talking. So obviously I mentioned Coulomb for the Coulomb model of static friction, but he's actually preceded by a Montagne. And pertaining to static friction in particular, there are two laws that they made regarding the maximum force of static friction between two surfaces. The first being best expressed in that law that I showed already, but that is proportional to mu s and Fn, the coefficient of static friction and normal force respectively. They also showed that it is independent of the contact area, in that you can take, for example, I'm going to use the brick on wood example again. You can take the same brick, you can orient it horizontally, so that's almost flat on the ground. You can orient it vertically. As long as it's the same normal force, the maximum static friction force is going to be the same. They also didn't have a very concrete explanation, or at least a very sort of valid one based on obviously the resources that were available at that time. And so when Hertz, Bowden, and Tabor came along with this sort of developing contact mechanics theory in the 19th and 20th centuries, they began to really sort of finally investigate how static friction originates at a very small scale from these two surfaces. I think the diagram here in this sense is really helpful. So Hertz, Bowden, and Tabor, sort of building on the work of each other, they found that while the static friction force isn't proportional to the real contact, isn't proportional to the apparent contact area, which is me at a macroscopic scale saying that, okay, I'm looking at this, I'm looking at a brick touching the wood floor, and I see the entire surface area of one face touching the floor. While static friction was independent of that, as Coulomb and Montagne found, it was dependent on something called the real contact area, which is where the two surfaces were actually very close together. So in the diagram on the right, as you can see, I might say that the apparent contact area between these two surfaces, if I really zoomed out, would just be the area of those two square faces, the area of each square face underneath. But the real contact area would be where those edges, asperities as they called them, were actually getting very close together. So with this theory of asperity contacts in place, that led to authors like Narayanan, Johnson et al., the DMT and JKR models respectively, trying to understand now, bringing in these sort of intermolecular forces like electrostatic van der Waals forces, understanding how they pushed asperities together. However, and this leads into our own research, they didn't investigate the force of static friction between two surfaces they didn't investigate the contributions of these fundamental forces to the force of static friction. In addition, because when you're considering the van der Waals force, which I'll bring in later, they didn't incorporate retardation effects or relativistic effects into their own calculations. So this leads us into our own sort of broad question. How do fundamental molecular forces contribute to static friction, not just adhesion, between two surfaces? Now, at a first glance, that question seems very hard to us, in that there are so many of these even subsets of electromagnetism that you consider: electrostatics, dipole, van der Waals, Casimir even. So how can I isolate like a single one of these forces just to study its influence on the static friction between two surfaces? A sort of test case that we came up with in order to study static friction where only one force contributed was van der Waals materials. Now, you might have seen them called van der Waals materials, 2D materials, layered materials even. The basic structure in van der Waals materials is that there's this large 3D structure, but as you sort of zoom into it, you'd see that it is actually composed of individual 2D layers. Now, these 2D layers are held together by van der Waals forces. You might ask, what are van der Waals forces? Van der Waals forces are the sort of resultant force from two atoms with induced dipoles interacting and being attracted. And the actual origin for these induced dipoles is quantum fluctuations in the electric field, which polarize an atom ever so slightly, inducing again polarization in its neighbors. Now, the 2D layers of each van der Waals material structure are held together by van der Waals forces in a diagram here. While each individual atom in the same plane is connected by stronger covalent bonds, that sort of weaker interaction between atoms in adjacent layers is the van der Waals force. And van der Waals materials have a variety of practical applications as well. You might have heard of graphene being this material with very low coefficient of static friction with all of its potential uses in nanotechnology. And their very low coefficients of static friction have made them what's called solid lubricants for several years, in that they're powders of, for example, an example of a van der Waals material that is discussed fully in this work is molybdenum disulfide. Often there's, for example, a powdered version of it that's poured on two surfaces in order to reduce the coefficient of static friction. Now, because it's the van der Waals interaction that actually it's the van der Waals interaction that's predominant between two layers of these materials, this essentially lets us say that this is a good test case for understanding the contributions only of van der Waals forces to static friction. So this leads us to our actually specific question. What are the contributions of Casimir interactions to static friction? The goal of this research is to understand how fundamental forces, but with the van der Waals interaction as a focus for this portion of the project, to better understand how these forces contribute to static friction. And in doing so, as a way to sort of quantify our hypothesis, we sought to derive an analytic expression for the coefficient of static friction that was based not on things like just the ratio of the maximum static friction force to the normal forces given by the Coulomb model, but instead on these sort of atomic surface structure properties. Now, our hypothesis was that these fundamental interactions, or van der Waals interactions, would determine the mu-s of two-dimensional van der Waals materials. However, we are not just considering, sorry, I'll say this before, we're not just considering the van der Waals interaction or the standard one, we're actually going to consider the Casimir interaction or the Casimir-Polar interaction, which incorporates retardation effects, essentially the time taken for the field to propagate from one atom to another creates an additional delay in the field, which generally reduces the magnitude of the force between the two. So to get started, what we had to do was model the way van der Waals materials looked. And just as a general sort of model for this, we used a model of two sinusoidally corrugated plates, which are corrugated in one dimension. They extend to infinity in both the y direction, which is along the page, and the x direction, which is into the page. In the z direction, they're separated by a distance a, just to give what the variables mean, which is the interlayer distance. In the right-hand picture, you can see that there's sort of comparison between our model on the left and the actual van der Waals material boron nitride on the right. A in our model, which is the distance between the midlines of the two sine waves, is equal to the interlayer distance of the two layers of HPN. Lambda, which in our model is the periodicity or essentially the wavelength of the sine wave along the surface, is equal to, well, we'll get into this later, but sort of the length of the periodicity along the boron nitride layer. H1 and H2 are the corrugation heights. I'll get into what that means for the actual van der Waals material later. The H1 and H2 are the corrugation amplitudes, how far each corrugation extends from the midline. And lambda, I already explained, but the wave number k is equal to 2 pi over lambda, just from the definition of the cosine wave. It represents the periodicity of the layers. As k increases, the waves become closer and closer together and more frequent. As k decreases, the opposite happens. And finally, the lateral displacement y represents the shift in the layer stacking, how far the top plate is moved a certain amount to the right in its sine wave with respect to the other plate. To calculate first the interaction energy between these two plates, we considered, as I mentioned before, the Casimir-Polar interaction. Now, the van der Waals force is caused by the van der Waals force is caused by quantum fluctuations. Sorry, but we are considering this force in the Casimir-Polar limit. Now, the Casimir-Polar limit considers, as I mentioned, retardation effects from field propagation delays, and the expression that we're using is
Ram, sorry to interject. Can you go to the previous slide?
Of course.
Yeah, sorry. So what is the okay. So fine, okay. So these two blue lines are nothing but the they're extending in the x direction, right?
Yeah, I think the model is kind of hard to follow from here just because of the perspective.
Fine.
So each set of two lines, so like the black lines here, these two, those represent one corrugated plate. Essentially, imagine like a structure that's sort of curving like this. If this is like an infinitely extending plate.
Okay. So it just represents the surface, right? I mean,
yes,
extending in the x direction. Yeah. Okay. I thought that maybe it is some kind of displacement of this, but no, that's not.
It's just that the two, each set of two represents surface. Thank you for the question.
Yeah. Thanks for clarification. Thank you. Go ahead.
So the expression that we use to calculate the interaction energy between these two plates is given by U equals negative 23 alpha 1 alpha 2 h bar c over 4 pi cube r to the 7th. This is the interaction energy between any two point atoms, where alpha 1 and alpha 2 are the polarizabilities of, the static polarizabilities of the first atom and second atom. As you can see, this expression, first off, the h bar in the expression shows the origins of the Casimir interaction quantum fluctuations. And then while the van der Waals interaction has a standard r to the -6 dependence, the Casimir interaction actually has this r to the -7 dependence because there's this additional incorporation of distance for the field to travel from one atom to the other. And we see the C incorporated along with that to essentially incorporate the relativistic retardation effects in that sense, because the field propagates at the speed of light. Now, we essentially integrated this point-to-point van der Waals interaction energy or Casimir interaction energy formula over the two plates. This obviously gives an integral over 4 variables, which are the x of the bottom plate, the y of the bottom plate, the x of the top plate, and the y of the top plate. And instead of solving these integrals analytically, we used a perturbative expansion with the sort of assumption that h1 and h2 are both much less than a, so that we can drop some of the higher order terms. So when the denominator of this expression in the integral, which essentially represents the distance between any 2 points along the two surfaces, when that is expanded using a Taylor series, we find that the actual interaction energy between the plates is the same as the interaction energy between two flat plates, plus these higher order corrections. So there's one plate that's completely flat, one plate that's a sort of corrugation correction. Then you have the second order terms, out of which there's one term with 2 corrugated corrections. And we use this perturbative expansion in the second order, and I'll talk about it a bit more later, which means that we dropped any of the terms that were third order and high. We're considering only the 0 term, which means 0 powers in H1 and 0 powers in H2. The 1 0 term, 1 power in H1, 0 powers in H2, etc. And then 2 powers in H1, so it's H1 squared times something, and then 0 powers in H2. Same for 0 2, just switch. And then U11, where there's a power in H1 in the expression for the energy term, that power of H2. So after calculating this out, computing the sort of broken up integrals which were done by the Taylor series, we found this expression for the total interaction energy per unit area between the plates. And you'd notice that there are 2 of these terms that have crossed out. There are only 4 total within the brackets. And that is because these leading order terms do not contribute to the to this interaction energy at all. The first order terms don't contribute because of the sinusoidal symmetry implicit in that one corrugated plate, one flat plate structure. Now, you notice that the first term in these brackets, so there's this obviously this term outside, which has units of energy, where sigma 1, just to be clear, is the polarizability per unit area. It's a polarizability density that we've defined. It effectively represents the dielectric properties, but it's not very important for this. And inside this these brackets, this first term, so this outside term, 10⁵, that represents the interaction energy between 2 flat plates. And now with all these terms that follow, these are the sort of obviously the second order corrections to this interaction energy, and they're dependent on H1, H2, A, and K, the variables I mentioned before.
Can I ask a quick question?
Yeah.
So for this U20, you're also gonna get a flat plate interacting with a corrugated plate.
Yeah, the exact structure of it is something that we were actually discussing some time ago. So the way the integral actually works out is that it becomes h1 squared cosine squared ky, where y is or ky prime, where that's the integration variable, over r to the 9th power. And the physical meaning of that isn't exact, since if the Casimir interaction is r to the -7, but our understanding, the way that we sort of phrased it, was that it was a flat plate, and then there's one plate with sort of, I thought of it as a sort of cosine squared polarizability, but I know that Dr. Shajish and Dr. Prachar also were considering it almost as like two corrugated plates. So I think the exact sort of physical interpretation of that isn't something I can quite put my finger on. I think it was just sort of it is the way that we thought about the correction terms.
Maybe I can say something here, Ram, real quick. So the term which is like U02, John,
Mhm.
think of it as the second order. There is only correction in the flat plate that you are considering. So there is a flatness
Yes.
to a plate, and then there is corrugations coming up because of the shape. And when you make that second order to that correction, consider only the second order part interacting with the flat plate.
So
That
it's more corrugated than
Yeah.
U11.
Well, you will consider, yeah. So the point is,
Yeah.
like, when you are doing the Taylor series expansion, like each term is more corrugated, like, so there is a
Yes.
slight difference on the first term from the flatness, then there is like more
Yeah.
corrugations because of that. So only the correction parts, we are not, the flat part is gone. Flat part is U00, right?
Yeah.
Yeah.
So I mean, would U30 still be there?
Yes. And that we are neglecting because it's perturbative. So it's small enough to neglect.
Okay.
I did, however, I'll say this just as you mentioned. I was presenting this at a science fair, and a judge mentioned that perhaps the third order terms, every odd order term, he said, for example, the third order terms, he mentioned that maybe it would be worth understanding whether they are zero, in fact, because he had this sort of explanation for himself that it has to do with the even nature of cosine, that when you have cosine, cosine squared, cosine cubed, and integral.
Yeah, I think one should mention.
Yeah, I recall doing this at a more generic level. Here we are in the Casimir polar limit, that the odd term comes out 0.
All the odd terms will be 0, yes.
Yeah, so the next one will be and actually we have gone on till the fourth term. We had to go to the fourth order because the third one was 0. Yeah, we have actually seen it, the third one also going to 0. Yes.
All the odd terms goes, and I think like probably the argument is related to symmetry, but there is no clear
Yeah, it's just
thought on that. Yeah.
perturbation. Yeah. So,
Just a minute, like, to make sure that whether I understand this correction term. So U00 is when there are no corrugations in both the plates. Am I right?
Yes, it's the most basic system. So two parallel plates with constant polarizability, their interaction energy. That is U0.
And they are not sinusoidal.
Yes, for the U00, there's no corrugation, not even a change in the polarizability.
Then U10 is the your say bottom plate is flat and the top plate is having a sinusoidal corrugation, right?
I think that was the sort of visual for it when we imagined it, but these are really just sort of correction terms, because powers in the denominator, as well as the fact that H1 comes up in the numerator instead of the actual distance, means that they're not physical corrugations in that sense. They're just sort of sinusoidal polarizability almost. The exact physical interpretation was just always hard to place my finger on. This visual that I gave here was mostly just to understand how one could interpret these terms.
Like Rishi, what may happen with the visual is that it may feel like the correction term has the complete corrugation on top of it, but it is not the complete plate there. It's just the first order correction away from the flatness. And that if that can, yeah. So visually
yeah.
drawing it out is a little difficult.
Yeah. No. I see.
And the reason why you're considering, are you just approximating some curved or some spiky material?
Actually, no. This is just for a sinusoidal material. It's that really the reason is that we couldn't compute the integral just exactly, and obviously there are numerical methods to do it, of course, but the sort of value was that also with the second order expression, as we'll see later, there's some beautiful simplification that happens, and it leaves an equation for lateral force, normal force in the US, not to spoil too much, that actually I feel like you can do a lot more analysis for than if you just sort of computed this integral standard way and maybe got some monster expression.
So this isn't specifically modeling the lattice that you
Yeah,
showed.
that's true. It's not modeling the lattice. I do bring up sort of later towards the end about how obviously this one-dimensional sinusoidal corrugations model might be limited, and how it's more useful to use, I bring up like an hexagonal approach. I will say that, like, for example, if you were trying to model a lattice, the Fourier sort of series of sine and cosine terms, we'll idea perhaps roughly an approximation of some one-dimensionally periodic surface, and that would essentially be just a sum of a bunch of these terms with some evaluation of the cross.
Okay. Cool. Thanks, Ron.
But yeah, just to finish off about the perturbative expansion, this means the simplest that we could have used to actually get the interactor entry from the corrugations had to be second order. If we just use the first order terms, obviously we would be left with interactor energy between flat plates, which is not as useful.
Yeah, I guess like one should consider this calculation as proof of concept. Like you were just trying to say that van der Waals or Casimir folder contributes to the coefficient of static friction. And if you really want to do a modeling and stuff, then you have to go with the roughness and everything, and then you want to get like little more. But whatever said and done, like I think any kind of surface profile, you might be able to like kind of write it or represent it as a Fourier series, and then you will be dealing with like all these kind of interactions with little more complicated sign functions coming into the integral. So consider it like as a first, like what you call first calculation to just show that, yeah, there is a contribution coming from this, this particular interaction.
No, it seemed, I mean, I think the motivation was that when you had that spiky material, you would get some like corrections that deviated from the Coulomb model. So
I think that also goes into like the asperity part, like with actual mechanics of it, edges getting stuck on each other. Part of it I didn't fully go into how there's obviously like much more mechanics-based reasonings for with asperities. If you have like rough edges, for example, just sticking out, like it's sort of stuck on each other, preventing motion.
okay, so that's not trying to capture. That wasn't. That's
yeah, in
just
fact, the plates are
general.
separated. They don't touch, and we get into that a bit later. It's mainly just thinking about it as sort of fully theoretically as we can.
Like what he was trying to emphasize earlier is that all the asperity related work, they actually use mechanical elasticity forces for this friction. So there is a push, and due to that there is friction. Here now this is not even a contact is necessary. So in that sense, van der Waals is a better sample to study in this case. When there are more asparatives, then actually the chances of physical touch is more. And then these are divergent, basically, these expressions. So we don't have very good understanding of that at this stage. So we would like it to be separated by a distance, and van der Waals materials works good in that. Am I right in saying that? Yeah. Okay.
Thank you.
Just to note, before I move on, is that can everyone see my cursor? Mouse.
Tell
Can I
that
see the
again?
cursor on the screen? Is it visible when I?
Yeah, very.
Yeah, I was going to highlight that. Obviously, U is the interaction energy per unit area is periodic in Y, and this term is relevant just for the next calculation. So with this interaction energy per unit area between the plates, we now calculate the lateral force per unit area, the force that's applied relatively along the plane of contact, and the normal force per unit area. And these are done by taking the gradient of the interaction energy, but for their magnitudes, the lateral force is negative derivative of U with respect to the lateral shift. The normal force is the negative derivative of U with respect to the vertical shift, or the vertical displacement, which is just A. So by taking this gradient, this is the expression that we get for the lateral force. This only comes from that last term, that U11 term. And so notice here, this is important, this is relevant for later calculations, that it's periodic in Y. So as one of the plates sort of moves over the other, obviously keeping it static, but if you were to like set up the system again and again with one plate moving over the other, sorry, no, not moving, you need to be careful about that. If you were to set up the system again, but you change the lateral shift for each one, this would be a sort of smooth sine function. And I didn't mention it in the paper really, but there's an interesting sort of correlation to this in that this obviously has to do with the periodicity of the structure. As you move, after you move a certain length, you have the same system again, so obviously the lateral force has to be periodic. And so if you're to look at sort of real life experimentation of materials where this is not necessarily just that smooth sine wave, there's actually this sort of stick slip phenomenon where they get this sort of, when you're graphing lateral force versus lateral displacement, there's sort of almost sawtooth like curve. I don't have like an exact theory for this, but maybe one could consider this as a sort of limiting case where that structure is so smooth that you end up with just a smooth sine wave instead of that jagged curve for lateral force versus lateral displacement. That's it for the lateral force.
I would like to make a comment on that. There was I think it was an experiment and a theory calculation in a very similar, more complete calculation involving not the Casimir polar limit, but the whole Casimir calculation. And in that, they argued that if you keep higher orders in this, then it's not sinusoidal. Then you start seeing that spikes. And they compared it with experiments also, because it was done in a group where they had the experimental facilities too.
Yeah.
So yeah,
That
just
was
comment on that.
Yeah, not done in context of the static friction per se, but yeah, it was a different kind of calculation with Casimir effect, which shows that keeping higher order terms will start bringing in more, like basically as you add up all the Fourier terms, it will probably start shifting the curve and then like making them more sawtooth-like.
So good point. Yeah.
Investigation.
So yeah, this sinusoidal is a consequence of your sticking to second order terms only, right?
Yeah.
Lateral is
That's-
sinusoidal.
Yeah.
Mhm.
Yeah, exactly. And then it starts tilting a little, at least to the next order, it tilts a little bit and so on. Yeah.
But
see,
just a moment. So actually, I'm still not getting. So you are obviously not really looking at the profile of the two surfaces, because that may be more complicated, right? The actual profile in X and Y direction is not sinusoidal. That's what you're saying, right?
I think
Yeah, go ahead, Ram,
I was
please.
going to say, so no, the profile of the two surfaces are sinusoidal. the actual physical, like the physical system we are setting up is two sinusoidally corrugated plates. I think what was just mentioned was that what I brought up is that the lateral force between the two plates is sinusoidal as a function of lateral shift. Because obviously, once you move a certain amount, you have the same system. They extend to infinity in both directions.
Why is the shift, right? Why is the shift?
Yes.
Yeah. And
And
of course,
so-
it is the profile is sinusoidal in the x direction, right?
In the y direction, we use y as the sort of horizontal x being into the page.
Okay, so in the y. So in the x, of course, these are the directions of constant phase, right?
Yes.
Okay.
And so yeah, Dr. Shawish then brought up how this might actually not be the case we consider, as shown in the paper, if you consider the full van der Waals or Casimir interaction, not just Casimir Boulder,
Yeah.
where you get this more jagged curve.
So x direction, of course, there is an exact phase correlation, right?
Direct, like the direction of the force?
No, in the x direction of the material, there is an exact phase correlation. You know, all the maximas and minimas, they match.
Yes, it behaves like all of them
Yeah.
rise and fall.
Exactly. Yeah. Okay. And like so, how realistically in this kind of graphene, this thing, how different it is from such a profile, sinusoidal profile?
Yeah, I guess like maybe Rishi, wait for it. That is an interesting question to consider in itself. Like, how do you model the 2D materials? Yeah, and there will be quite, I think questions, objections, all that to that. Yeah.
Yeah, we're going to address like the surface approximations that we make of the materials. But for now, we're just talking about the general case still, two corrugated plates. And for the normal force, you get a much bigger expression than what you see pictured here, obviously. Every term here has an A, taking the derivative gives you this sort of much larger expression. And I think our initial reasoning for approximating it only to this first order term, to be clear, this is the normal force between two flat plates. Our reasoning for approximating it and only using, sorry, the cursor, right? Only using this term to calculate the normal force. It was a lot, I think, less rigorous initially in that we were just saying we're using the perturbative approximation, though for the later terms will be small. But Dr. Shajish brought up that actually, if you wrote this in terms as, normal force between two flat plates times 1 plus some higher order terms that are of second order in H over A, then what happens is that because this normal force is in the denominator, you Taylor expand that as 1 minus x. The remaining sort of lateral force over normal force, which I'll get into afterwards, actually is of fourth order if you do consider those second order contributions, which is why we decided to use the 0th order terms instead. Let me know if that doesn't make full sense. I think maybe I can explain it better.
Yeah, so maybe a better statement will be that the coefficient of static friction that you're going to derive using that FL max over Fn is correct up to the second order in H1, H2. Probably that's a better way of stating the result. Yeah. And you can keep higher order terms, but if you want to keep higher order terms in the normal force, then you have to go out to a higher order term in the lateral force also before you can do that.
That makes sense. See, so for the purposes of the μs calculation, the normal force is approximated this way. And so, speaking of which, this is where we need to sort of discuss how we found μs, because part one of the goals was to make an equation or expression for μs from this. Now, the Coulomb model of static friction gives that, so in a picture there, Fs max equals μs times Fn. So if we were to get an equation for μs just from that, you'd rearrange, you'd say μs equals Fs max over Fn. But our sort of hypothesis here in this entire thing is that the static friction force itself is caused by the lateral component of the Casimir force between these two layers. So we replace that Fs max by FL max just by virtue of what our hypothesis is. And if you want to find the maximum of the lateral force, which is a sine function of Ky, you simply take the maximum value of that sine function, which is 1, and then multiply it by the rest of the expression. Now, when you divide through by the normal force after doing that, I think you see this sort of cancellation happening already with these. You get this sort of very clean expression from US, I'd say, in my opinion. And just to point out a few things immediately, notice that it only depends on the distance between the layers, A, the height of the surface corrugations, H1 and H2, and the periodicity of the surface corrugations, K. K is the wave number, to be precise. But if you want to actually talk about certain ratios of lengths, then you describe it as a function of the dimensionless parameters Ka, which is roughly the ratio of interlayer distance to wavelength. Then you have H1 over A and H2 over A. These are the ratios of corrugation amplitude to interlayer distance. Notice though that while the lateral force and normal force and even the interaction energy have the sigma 1, sigma 2, which as I mentioned before represents the dielectric properties of the material, these aren't present in the expression from US. It's not dependent on the polarizability and the dielectric properties of the material. Give me a moment, sorry. I have some allergies. Apologize.
If the corrugations are larger than the separation area, and then
As far as they don't touch, they are good. So you can go in them, but they shouldn't touch each other.
Sorry.
yeah,
I think
I
the
see.
question was, should the heights be, how did you phrase it? I think you phrased it much more efficiently.
less than the separation distance.
Yeah.
So in the sense that if you move it, you might just bump into the,
Like, should the distance between the plates be smaller than the sum of the height of the corrugations?
So
Is there a requirement like that? That's what John is asking.
yeah, I mean, I don't know if you mentioned, but that's precisely I think on the next slide about that when I'm talking about graphing. I guess I'll mention that now. I guess I must just go into it. So this will be on the next slide. About the dimensionless parameters, I think this is important because this is what we're going to use for the graph. So this is a plot for mu s with respect to Ka. Ka, as I mentioned, is roughly the ratio of interlayer distance to wavelength. So you can take a look at this graph just before I say anything. All right, I'll get started. So notice first that there's this constant maximum of around 2.93. And we're still studying Van der Waals materials. So what I wrote was that mu s is always maximized for Ka is equal to 2.93 in Van der Waals materials. Generally, just from doing these calculations, Ka is closer to 10 than it is to 1 in terms of the ordering. It's for the Van der Waals materials that we discuss, it's around 6 to 8. As you can see here, these are where the values of Ka lie on the graph.
And K is the 2 pi over lambda, right?
Yes, so I wrote in ratio, it's 2 pi times the ratio. It's just what matters in terms of the scale of lengths for me to see. Now, I understand that the reason that I use multiple graphs might be confusing. If I were to give you, for any material, H1 over A, H2 over A, and H3 over A, and you want to use this graph to find it. First, you take this expression and you would just plug in what H1 over A and H2 over A are. And that gives you one of these curves. So if I say H1 over A equals 1/4, H2 over A equals 1/3, I would plug it in and it would probably be somewhere between these black and green curves. You get curve of mu(s) with respect to Ka. Then if you want me to actually give you the coefficient of static friction for that material, then I would actually have to select the value of Ka along the x-axis and see where mu(s) is on that curve. Now, an interesting question is then, since it's always maximized for the same value, what is the actual bound of the coefficient of static friction? Because, I mean, obviously, there's this limit that they can't be like literally going through each other. But even if, as you were mentioning, how it's like, what if H1 and H2 sum to greater than A, or the interlayer distance? Now, I did show this graphically. I guess maybe it would have been nice to include it. But you can have like H1 plus H2 greater than A, but the corrugations are shifted in such a way that one locks into the sort of groove of the other, where one is sort of reaching downward. The same thing is happening with the bottom, in a way that keeps them separated, even though H1 plus H2 is greater than A. And that's true. We have to, if we want to sort of bound the coefficient of static friction more reasonably, if we say that H1 plus H2 is less than A, or that both H1 and H2 are, and the way we phrased it was H1 and H2 are both less than A over 2, then the maximum coefficient of static friction for these van der Waals materials is 1.29. And that is the maximum that's achieved when H1 equals half A and H2 equals half A. So they're basically touching at that very, very small.
So given any van der Waals material, if they are not allowed to penetrate into each other, you cannot have a coefficient of friction greater than 1.29. It's a bound you're putting on. Okay.
If there are no other questions, please.
Okay.
So yeah, this is where we bring up the van der Waals material portion of our project. So to sort of validate our expression and sort of see how it compares to reality, we had to first apply our sinusoidal corrugations model to the structures. Now, I think I don't remember who brought up the exact like how this compared to the structure of van der Waals materials. Anyone remember?
I sort of pointed it out, so it's okay.
So if we take, for example, graphene, which is portrayed in these two. Graphene is a 2D material, which already presents a challenge in that there is no sort of change in slope along its surface that lets us use a sinusoid. And it is hexagonal. There is not a one-dimensional sinusoidal corrugations, obviously. No, there's not a one-dimensional sinusoidal corrugation. There is sort of hexagonal corrugation instead. So to actually incorporate our model, we're making yet another approximation. So it is true that if we were to take the short diagonal path, like if you were to look at the direction of one of the short diagonals and treat that as your direction for the sinusoidal corrugation, as shown by this axis, that path doesn't, obviously it is periodic. This length and this length are going to be the same. What that doesn't account for though is that these, like in the x direction, you're not having a constant height as you're moving along the surface. It's actually doubly periodic in the x direction, considering, for example, long diagonal, then side length, long diagonal, side length. But our goal was really just to apply our model and see what it showed. And so we chose the short diagonal path for, I guess, plugging in our values for periodicity. And we said simply, our model is unable to capture this double periodicity at the moment. I will discuss towards the end how these doubly periodic structures can actually be incorporated into our model. But this is what we did so far. Now, if we were to look at a sort of profile view from this, the issue of corrugation heights come up, right? Because the surfaces are actually not changing in height. But when you take a look along this sort of the profile of the short diagonal, what we decided to use was the atomic radii as the corrugation. Now, this obviously is perfectly sinusoidal for when you use like a sort of spike at one point with the atomic radius, but it was a way for us to actually incorporate this corrugation into our model. So just leave those diagrams for a moment. Are there any questions about that, at least for the application? No,
No.
then yeah. So that's a bit of a spoiler, actually. I'll say this before I go to that slide. When we calculated the interaction energy and the coefficient of static friction for van der Waals materials, and we compared them to previous results, it's shown in the next table. You might ask, why did we calculate the interaction energy in the first place? And the reason for that is, sorry, if we only calculated the coefficients of static friction, how would we know that it's not just a fluke? How do we know that our model is correct and that we're not just getting these proper values? Because by some error canceling out with another error, we get the right result. The interaction energy calculation in that sense allows us to sort of verify that our model is on the right track, and it validates the use of the coefficient of static expression to actually compare. So now I'll actually show the results. So I'll just leave it also another second just to take that in before I start explaining things. All right. So the three van der Waals materials that we calculated μs and the interaction energy for were graphene, hexagonal boron nitride, and black phosphorine. Graphene and HBN have very, very similar structures. They both have that hexagonal 2D layer nature. Black phosphorine is a bit different in that it actually displays corrugations along its height as you go along one of the directions. So you notice first, just looking at the interaction energy expression chronologically. For graphene, we find strong agreement with at least previous density functional and Monte Carlo calculations. For HBN, although our value is similar to one of the values that is in that range, that was done using local density approximation, but we do have at least one result that is very close to our own. It is true that there are values in that range that are higher, they're the same order or higher. Our explanation for that isn't like fully complete, but one of the lines of reasoning that we use for this is that HBN, when we are talking about the corrugation heights, we treated it essentially as if it was a layer of nitrogen and a layer of boron on top of it, in that we didn't incorporate the fact that there are different atomic radius heights in the same layer. And this wasn't a very, very bad approximation in that the two lines of atoms that are directly above each other are opposite, but it is an approximation nonetheless of the HBN surface. And finally, for the black phosphorine interaction energy, we do have two results from the literature that are of the same order as our own. And all the values reported in the right-hand column are theoretical. We weren't able to find an actual study of the interaction energy of just the bilayer, which is important. These calculations are for the bilayer or for the slightly related exfoliation energy, but we didn't want to include like the binding energy, for example, just taking a bunch of sheets and putting them all together, seeing how much energy that took. And now for the expression for μs that we derived, which is really the sort of comparison we want to make, we find a general agreement for graphene and hexagonal boron nitride. Same order, very close even, 0.053 for graphene, 0.07 in the literature. Similarly, 0.076 for hexagonal boron nitride and 0.07 for in the literature as well. For black phosphate, on the other hand, we see that we did get 0.172 as the coefficient of static friction, but there isn't a study of the static friction coefficient between layers of black phosphate in the literature. It is an emerging field of research, so use of black phosphorus as, for example, a lubricant or an additive in two surfaces has been studied, but just taking 2 sheets of black phosphine and seeing their coefficient of static friction hasn't yet been done. So now that I've brought up the results, I'd like to discuss some applications of our work, some ways in which this model might be limited, and how these limitations could be overcome in future work. So as I discussed, van der Waals materials are gaining a lot of interest and traction in nanotechnology, specifically for the 2D nature of their layers, which is already incorporated into our model. Now, with this expression from US, an engineer could essentially predict the static friction force in a nanomachine as long as he's given the normal force between any 2 parts. And this would be extremely useful in design, in the sense that you'd be able to understand just with how much force something needs to, with how much force needs to be applied to an object in order to make it slide past another. And again, in nanotechnology, since they're facing issues with static friction impeding the motion of small parts, this is just essentially a useful tool to predict that before it happens. Not only that, though, but one thing we discussed in our paper is actually engineering a value of US by choosing certain materials that were, in a sense, obeyed certain properties. To go back to the graph, one thing that I wanted to discuss was that notice that while US is maximized for Ka is equal to 2.93, if the interlayer distance is much greater than the wavelength, which makes sense, this is this far limit here where A over lambda is very large, then you'd expect separated surfaces to have very low friction between them. But we also find this interesting result, where as Ka goes to 0, the coefficient of static friction is also minimized. And for this, I thought of it more in terms of K than I did for A. So I was thinking about if we kept A constant while K went to 0 infinity. As K goes to 0, that corresponds to lambda going to infinity, right? Because K is the inverse of lambda. And that would correspond to a corrugation that moves so slowly that the plate essentially behaves as a flat plate. On the other hand, as K becomes very, very large and these corrugations become very frequent, the surface becomes very, very sort of rapidly spiking. And in that sense, one could imagine the peaks of each corrugation being close enough to simulate a flat surface in that regard. And what that might suggest is that there's this role of surface smoothness in implying US. While this was previously suggested by the theories of, for example, asperity contact, where smooth surfaces didn't have the asperities to actually create this large static friction force, I think we might have an explanation for this theoretically, in that we have essentially shown that with low values of K, large values of A, this exponential behavior gives it this minimum at these 2 endpoints instead.
So in the literature, do they see these 2 effects on the 2 extremes, both going to 0?
I think I looked for it. I remember looking for it. I didn't find anything very concrete on this. I know the smooth thing is certain just by the theory of asperity contact. If you're saying that friction comes from asperity interlocking, then it must be that without these rough asperities that the friction is generally reduced. I haven't seen anything with the actual more interesting one, where the peaks of the corrugation are close enough together to actually simulate that surface in that regard.
Yeah.
Maybe I can look a bit more to see whether.
Yeah, good point. Yeah.
But yeah, that has a variety of uses in nanotechnology, where someone might be trying to choose a certain material with values that minimize static friction. And I gave this example of reconfigurable logic gate, recent research where there are these layers of van der Waals materials that are stacked in an electronic device, which makes interlayer static friction something that comes into play that must be treated. But it's not just van der Waals materials that this could be applied for. If we could incorporate electrostatic effects into our model, then a similar expression could be derived to calculate maybe for metals in the field of nanotechnology. And that could have a variety of more uses beyond just this sort of focus field where van der Waals materials are really of interest. And this is where we talk about surface structures. Just for those who are wondering.
Just a small question, Ram.
Yeah.
So if we find experimental evidence of vanishing of US for small k and large k, in some sense it would be a validation of this model, right? Your predictions that US would be vanishing for small k and large k, right? Yeah. So in some sense it would be an evidence that the higher order contributions of corrugations at higher orders in H1 and H2 are not important, right? Because this result holds true only in the limit where your the lateral force is sinusoidal, right? This result, if
I think that might not be the case if it's a similar function multiplied by any periodic function, in that the maximum of those might just be, the maximum of those of each of those periodic functions might be just one. And then when you multiply that in, you get a similar expression, because we're really considering the maximum lateral force, one that doesn't vary with respect to lateral shift.
I mean, intuitively, I expect that this should be independent of the order that you consider. You know, logically, it makes sense that if you have corrugations that vary very widely, you know, peaks which are very closely spaced, you should simulate the flat surface. And if you have the corrugations that vary very slowly, so that effectively becomes a flat surface. So it should be independent of the order in H1, H2 that you take, right?
Yes.
This result should hold independent of the order that you take in H1 and H2, right?
I will say that one thing just I remember from the math of doing this is that the reason we get this negative exponential behavior here, and you can see in this graph, polynomial rising, exponential decaying, is each term, because it has this cosine over r to the some power, you end up with the Bessel function, k sub something over 2 of Ka. And it's actually expanding this Bessel function in terms of the exponential and polynomial that gives this exponential behavior that we see here. I think an interesting question to your point would be to see, does the fourth order term have the same exponential times polynomial behavior? Because the results for this, actually, I'll say this, from doing the math, it's not as much shown in the paper, but the results for this come out like surprisingly nice when you expand the Bessel function again, in that you can get this nice polynomial multiplied by e to the minus Ka, and perhaps that just some specific case of a more general result that you could show with this.
And this this point that for large or for small wavelength, this is going to 0. This was not highlighted in the paper, correct?
It was, I think. Further down, I think the sentence.
It was.
Okay. Sorry. Okay. That's good then. Yeah. Okay.
But so yeah, for the limitation of the surface structures, since this was brought up, the left, I think, is a better representation of how our model actually looks. This is how one of the plates would look. You see this sinusoidal, one-dimensional corrugation in one direction only. But obviously, that isn't holding up perfectly for hexagonal structures. And this is one of the models on the right that we considered using. It has a much more sort of hexagonal shape because it incorporates corrugations in not just the y direction, but the x direction as well. And you can see here that there's this x dependence now brought in here. And from this minus 1/2 root 3 over 2, you'd guess that there's some sort of 60-degree angle coordinate system that we're considering, which gives us this hexagonal shape. Notice, however, that this isn't perfect for showing hexagonal structures, in that we have these sort of spots in the middle that are also being treated as atoms. So while this may be something to consider for future calculations, as in whether one could integrate this as well, it's not perfect still. Maybe there's some term you could subtract out just to get this one in the center away.
Yeah.
Maybe a delta function peak there or something like that can be subtracted.
So we couldn't model a hexagonal lattice. Huh?
Yeah.
Yeah, good point.
And I mentioned this before, but when we're obviously using Casimir polar limit, we're only considering the zero frequency components of the polarizability, so there isn't this integral over frequency. And if we were to go beyond the Casimir polar limit and incorporate these frequency dependent contributions of the full van der Waals interaction, that might make, for example, the interaction energy more precise, or it's like more accurate when compared to previous results. So to conclude what our research did for static friction, we made a simplistic model to calculate the coefficient of static friction in van der Waals materials, done entirely using first principles calculations. All this work was done on hand in the classroom library. We only used Mathematica really to calculate it for these specific materials or check our results. We've shown that for the system of corrugated plates, even not considering static friction entirely, the leading order perturbative terms in the Casimir interaction energy don't contribute. And this leaves open the question of whether it's just the leading order or whether there's the odd order terms, all of them evaluating to zero, as Dr. Shah just said. He had seen in some system before with the Casimir interaction.
I think the odd orders will always go away. Like that has been checked up to the fourth order, so like first order, third order.
Then, like for static friction in particular, we found that μs is independent of the stacking configurations to the second order, in that it doesn't depend on the lateral shift, or the dielectric properties of the material, which is really the sort of significant part, while it's completely determined by the geometric properties. And that's a very sort of interesting conclusion when you think about it. I started off by saying that μs is determined entirely by the material pairs and not anything else. Yet it seems that it's not even determined by that. It's really determined on how they're shaped. Now, it's not, obviously every material that you pick has a very sort of fine structure. It's hard to modify at that scale, changing the literal distance between each atom. That's a very sort of fine result balancing forces. But it is interesting to consider that, say we generalize this result, we found a similar thing for electrostatics for the full van der Waals contribution. Is it possible if I took two ice sheets and I put them together and I change their surface in such a way that makes them interact like metals, then could you essentially, would it be that hard to slip on some ice? And perhaps there are a variety of practical applications to go from there as well. People slipping, just an interesting thought. And using this result, our result from μs, we predict the maximum value of 1.29 between van der Waals material layers. I checked this in some literature just to see where these van der Waals materials generally have static coefficients of friction. Not all of them were reported, of course, but all the ones that I found, at least, were less than 1.29. Shows maybe some promise. But I think that with all the approximations that we've made, I don't think there's a really error that we can put on this or say that it's definitively correct. And so as for the application of this result, I think nanotechnology is really the sort of key here. Not only are they facing problems with static friction, but this can even sort of let them go beyond that, change static friction to suit their needs, even maximize it if certain parts can't move past each other. And as for how this work could be improved further, further calculations, further sort of checking of the results, really I think the surface profiles and the calculations of other interactions would make this much more complete, in that we wouldn't have to say that we're choosing the sort of arbitrary one-dimensional sinusoidal corrugation model and forcing it really to fit the surface, and rather using some combination of cosine terms, which would give a similar result to this U, and seeing how that might lead into a different result. And that would allow this model potentially to be extended to other materials. And even, for example, like the conventional materials, there might be some research worth exploring there, where you're considering all the sort of variety of interactions between them, seeing how each one contributes differently to static friction and the coefficient of static friction. Yeah, thank you. I think that was all I had planned. So, in case there's a question.
Thank you, Ron.
Good job, Ron.
Could you go back to the slide, Ron, again, one more time? I want to ask the table.
Which one?
Table, basically.
Yeah.
So the result for the energy calculation, which are reported, are they reported for the phosphorine? Like, I mean, remember we talked about this, like this is the binding energy versus the exfoliation energy.
Yes,
Do
my
you
understanding is that that's hard.
Go ahead.
It's like ask you mean like ask for like which ones these are saying, right?
Yeah, which ones are the reported values in the last column?
My understanding was that the top one was the bilayer and the bottom one was the exfoliation energy.
The top one is by binding, and the last, no, that's
I said the top one is the bilayer like interaction.
okay, bilayer interaction, which is much more closer to whatever we are kind of talking about. And the lowest, like the phosphorine one is?
Sorry, I don't know if you heard, maybe I didn't say that correctly. What it was, I think this 83 to 127 is the one that's the bilayer actually. And the
that one is bilayer, and the other ones are?
You mean the bottom one? The 150?
No, the whole column. Can you tell like the calculations are done only for the bilayer or?
Yeah. So everything, these three are all interaction energy calculations of the bilayer interaction. That's what it is. They're using density functional, however they do it. It is with black phosphorine. Once again, yeah, this was a sort of odd one out that there isn't a lot of research on the bilayer system, black phosphorine, their friction that I have seen. So these ones are different. So this is bilayer exfoliation.
And these are all like theoretical results. So you have not reported any experimental result on this last column, right?
Because I haven't found experimental determination of bilayer interaction energy. At least when we were looking for that, we weren't able to find it. Even the binding energy is felt very recent when we saw it.
Yeah, I mean, would you like to comment on the fact that why the graphene and boron nitride are lower than the reported values and the phosphorine is higher than the reported value? Or like, I mean, it's okay either way.
My guess is the dielectric constant that we, the fact that we use the dielectric constant for calculating polarizability. It was very sort of, I think it was simplistic the way we did it. Maybe there's something more sophisticated we're supposed to do. But again, simplicity is sort of the theme of our project, if you want to call it that. But a comment on it just for the people who weren't there. I mentioned that in the beginning that the interaction energy for 2 point atoms is determined by their polarizabilities, specifically the product. And that means that we had to find the atomic polarizabilities of graphene and HBN, which we treated as homogeneous. And what happened was for black phosphorine, again, we weren't able to find a value for its polarizability. It might have been there in the literature. I felt like it should have been there, just because it's been known for some time, right? So, correct. At least since a couple of decades ago. I expected it to be there, but it ended up not. At least when we looked, we weren't able to find the atomic polarizability of phosphorine. So we instead used this relation between the dielectric constant and polarizability, epsilon minus 1/4 pi. And we used that instead with dielectric constant of phosphorine. And we got a, I think for that kind of approximation at least, it's a reasonable degree higher.
Yeah, I'm not saying the results are off. I'm just pointing out the difference between the first two versus the last one, where we are having a higher value than reported versus, because all the things that are done on column 4 are most likely done using the density functional or Monte Carlo simulations, right? So they are using like a modeling of like individual atoms or in the structure when they're doing it. So, and I don't know, the other limitations of density functional theory and Monte Carlo simulations that they are doing is they cannot go beyond a certain separation distance. So they can probably maximum do, if I'm not incorrect, I don't know. I don't think they can go beyond 20 or 30 angstroms as far as the separation distance go, which is another differentiating thing, that we are not talking in that separation distance limit, because that's where most likely they are only seeing the non-retarded van der Waals effect. And actually I should take back, because some effect of non-retardation deviation starts coming up the moment you start reaching the 20 angstrom limit. So there will be a deviation, but it's still not as remarkable as what you will see in the Casimir-Polder limit that you are calculating. So that's a difference that I can see. But I was like just curious, like, well, why like one of the values reported are higher than while the other ones are all consistently like lower, the two of them. So that was probably one of the other thing which I find interesting, is that graphene and boron nitride having at least the reported mu sub s is exactly same to one significant figure, while we do see a slight difference.
Which one? Oh, what you see? What was the exact reason? It's very minute as well, because I think it has to do with the atomic radii. Boron and nitrogen having a larger atomic radii is what mathematically you'd say makes the difference. But if you're to actually compare them, almost all of their geometric properties which determine mu_s are of the same order. We say like graphene, the radius is 0.91 for HP, and it's 0.92, 0.98 respectively. A is very, very close. I think it's also that the A might be playing a larger role. For graphene, we said 3.42. For boron nitride, we said 3.32. So there's like 0.1 difference. I also think now that you're asking this question, what was the exact nature of it? These kinds of simulations, I think a lot of them just like find a value, I think, of graphene when they're, let me think of this. Yeah, I feel like a lot of them might be using a value of the graphene interlayer distance that's close to 3.35, because I feel like that's almost the standard distance. Whereas we took that range, 3.35 to 3.49, and we just took the intermediate value as a way of saying we're not choosing any one specific value. I think if we did 3.35 instead, we'd be closer to that value, because as A goes down, US increases.
Makes sense. Yeah.
Hi, Ram.
Oh, Dr. Vijay.
Yeah. This is Rishikesh here.
Oh, this is Rishi. Sorry, that sounded. I thought that Dr. Vijay had joined the call for a minute, because that sounded so similar.
Okay. Yeah.
Sorry.
First of all, congratulations on a very impressive presentation of a very complex subject, and I think you did it quite lucidly. I think if I were not to see your video, I wouldn't for a moment feel that I'm talking to somebody in the 12th grade. So I think kudos to you and your team of mentors. I think
it's a lot. It's mostly they helped me so much with this sort of throughout. I had to learn a bunch of stuff.
No, but I think it's also a good fortune of your mentors to have found someone who can match the wavelengths with them, who can be in phase with them. So I think definitely, far more congrats to you. And of course, I know your mentors and they are incredible people. And great work, actually. I really enjoyed your presentation. Just want to have some clarifications for myself. So when you presented this expression for U, the potential energy, so does it take into account your and even the previous slide?
The first expression.
Yeah. So since you're doing it in the constant regime, so are you calculating some kind of expectation values? Finding the expectation value of the U and also for the force?
No, are those statistical terms? I think I've heard them before, but I don't know the exact meaning. Yeah, but we aren't. No, we simply calculated U just by plugging in values.
These are, I think I can try to answer this. These are all second order correlations between the two fluctuations in or one point on the first plate and the second point on the other plate. All quantum fluctuations and the correlations between them. In field theory, that will be the one loop diagrams, all one loop diagrams. So that's taken care of. And in the extreme limit, where where we are saying that the what's the limit? All the frequency is set to 0. Yeah. So we have this frequency and k dependence in our field theory diagrams. We are setting them to the extreme case where everything is 0. Omega is set to 0. That's what brings in the simplicity. So it is non-perturbative in the sense all the loop diagrams are kept, but then it is on the other extreme. We are also saying that it is omega equal to 0, and which is all consistent in a certain regime.
Omega for what? Sorry.
The frequency. So now I can try to say this. So now suppose there are 2 points, let's say, I typically say 2 atoms, and both are neutral to begin with.
Yeah.
And now for various reasons, they start having polarizations. The positive and negative signs just, they start polarizing themselves. And they are basically random polarizations. And these polarizations can be characterized by a frequency, which is all frequencies, 0 to infinity. Now this is oscillating or fluctuating. Now this will try to fluctuate the second atom with the same frequency. So there will be some resonance effect. But if we take care of this effect on the other, that is what we mean by correlations, and then it coming back and affecting it itself, that requires the fact that the distance and the time it takes to come back has to match with the physical constraints. And that requirements basically, as this goes farther and farther, allows you to bring this simple formula in there. It's an extreme limit, but based on our experience in various systems, usually it captures about 80% of the effect. Let's say 75% of the effect if you want to be conservative.
So basically, of course, since it's a calculation of the correlations between these 2 fluctuating atoms, I mean, fluctuating meaning their polarizations are fluctuating at a given frequency, and you're looking at the correlation. So, and it's a theoretical calculation. So, of course, it captures the sense of the quantum mechanical expectation value and the force is calculated. Okay. And so how different it is, like somebody who is completely novice for this. So, I mean, I remember there is an expression for the Vanderwaals. There is a so-called Leonard-Jones potential, 612 potential.
Yeah.
Between two atoms, 612, and this is R7.
Yes.
So that's the difference of 2 terms. And I think that calculation also must be quantum mechanical.
That's correct.
Yes, correct.
But that does not take care of this
Retardation.
retardation. Like now what we are doing is that it says there is the speed of light has a finite speed.
Yeah. Hmm.
In van der Waals equation, when you write 1 over r raised to 6,
Hmm.
that condition has not been put. It is instantly interacting. That's instantaneous.
Mhm.
And that does not allow you to put in this extreme limit. So in all those expressions, you will see a C1 sitting on top, which is usually a parameter.
Hmm.
And that basically is the frequency integration. There you cannot approximate omega to be 0. So this
So you
one
have
is
to- You have
is
to factor in the retardation in order to take the omega to zero limit, you're saying.
correct, exactly. So it's a price you give. I mean, it is not the best. Both have advantages and disadvantages.
Because I wouldn't expect the retardation to play a significant role here.
Yes, it
Right?
should not. It should not. It should not. True.
Yeah.
True. So van der Waals is sufficient, but this is an easier expression to work with. Like this is a 1 over r raised to 7. You can almost bring in all your ideas of electrostatics. Integrations goes through. So as far as simplicity in math goes, tediousness goes, this is a big advantage you gain. The other one can be done. So in a more like if we have more time and
Numerical
background,
calculations, I guess.
that whole calculation can be done, but then you cannot do complete integrations there. Then you have to use
Numerics, yeah.
numerics has to be brought in. So yeah, both advantages and disadvantages in there. And material properties are frequency dependent. That's you have to go and get it from a table. So a lot of baggage to carry. This is a simple, that's what Ram is pointing out, that the theme is simplicity, that with a very simple model, can you predict a reasonable? And it seems like the first significant digit can be captured.
Yeah, you are in the ballpark of
Ballpark.
sophisticated calculation,
Exactly.
Mhm.
So,
Exactly. Which
so
is
that's-
remarkable if you
That
see.
speaks of the robustness of the approximations and calculations.
correct.
Yeah.
Yeah.
And all in all, it's a beautiful illustration of what's collaboration with a 12-year student can lead to. If both the sides are they give the 100%, then what can it possibly lead to?
Yeah, that is true. I mean, I think Ram is an ideal student in that sense, that he was able to work through it.
Thanks.
That
Okay, Shadesh, actually, I'll have to leave.
Yes.
I have to go somewhere right now. So it's, in fact, already I'm a little late to leave. So I'll
Thank you for
leave the.
coming. Yeah, I appreciate it.
Yeah. Thanks. It was really, I enjoyed your presentation, and it was a very lucid, I mean, you were very clear in your presentation. I mean, it's one thing to know, and it's quite another to put it across in a very clear fashion. So
Mhm.
thank you.
Thank you.
Yeah.
Thank you.
Thank you.